Hello, this is Simon or Z530807, and this is the recorded voiceover with the solutions I had for the bonus mark question number 1. So I've drawn a little diagram to the top left corner, which is a direct copy from the question itself. I've outlined that what we are searching for is the distance from shore to the furthest range that the projectile can hit using our angles. So I'm just going to have a look at the question 1 now. So it's asking us to calculate over what distance to the right of the mountain a projectile cannot hit. This is given that it must clear the 1800 meter height of the mountain. And so we're looking at the distance from shore in which the vessel to the right is protected by. Now to start with, we can see that on the top right corner where it says distance r question mark, it states that it's either the range of our delta h, which is our first projectile angle, or the range of delta L, whichever one is fitted, take away 2,800 meters, which is the distance from the origin of the projectile from the x on the x-axis, which is the sum of 2,500 meters and 300 meters, which is the distance of the boat shooting the projectile to the height of the mountain, plus the distance from the top of the mountain to the shore. And here we have below the diagram, we have the three kinematic equations that we are going to use to solve for this. So we have our position function, x of t is equal to a half a t squared plus v naught t plus x naught. Velocity function, v of t is equal to at plus v naught, and the at is a constant, or if we define it in terms of the y-axis, it is equal to minus g. To the right side, we have our triangle, which defines our initial velocity for as it's in x and y components, where we can see that the resultant vector of 250 meters of the initial velocity can be broken up to its x and y components by simple trig rules, which v of x, which is the initial velocity in the x direction, is 250 cos theta, and the initial velocity in the y direction is 250 sine theta. Now, the first premise we should understand is that the projectile must pass the mountain height of 1500 meters, and we know from the diagram that the time of the range 250 meters in the x-axis is equal to the time of height, in 1800 meters, that is. I wrote that wrong. The time of height in 1800 meters, which is the height of the mountain. So, the first thing we do is find the time of range for 2,500 meters, then sub it into the time of the height at 1,800 meters. Sorry that it's written wrong. I don't know where I got the 5 from. Using the position function, we should notice that the horizontal velocity is unaffected by any effect of gravity and therefore stays constant, which renders the acceleration equal to 0. And we'll use our frame of reference to state that it was also launched at a x0, or an initial height of 0 as well. From there, we are given the the positional range of 2,500 is equal to the initial velocity times the time peak, because time peak is the time it takes to scave 2,500 meters. Now we can rearrange this equation by substituting in v naught in the x-axis, which is our vx, and multiplying it by solving for time peak. Therefore, some rearrangement, and you will get 2,500 divided by 250 cos theta is equal to time peak, which you can further simplify to 10 over cos theta. Now we substitute this into our time of height for a y position of 1800 meters. By doing this, you see below we have y of 1800, which is a position, is equal to minus a half 9.81 times 10 over cos theta squared. 9.81 is our acceleration, which is minus g. T peak is substituted in for t, plus 250 sine theta multiplied by 10 over cos theta, which is our time multiplied by initial velocity y. Now, off to the right of that, we can rearrange and substitute in for our values. 1800 is equal to minus 4.91 times 100 over cos squared theta, plus 2500 sine theta all over cos theta. further rearrangement, you can use the useful trig identity to the top right in the little box, which states that tan theta is equal to sine theta all over cos theta. And just on the bottom of that, we apply it so that we get 1800 is equal to minus 491 all over cos squared theta plus 2500 tan theta. Now, moving on to the next image, we have here the same equation we just had initially from a while ago. And this time we are now going to solve for theta. So first of all, we let the equation equal 0. So we move everything on the right side of the equation to the left, which will give us 491 over cos squared theta minus 2500 tan theta plus 1800 is equal to 0. Now we want to apply trig identities to turn cos squared theta in terms of tan theta. And we can see again from the top right corner of the box that sec theta is equal to 1 over cos theta. And we can apply that to the 491 to give us 491 sec squared theta is equal minus 2500 tan theta plus 1800 is equal to 0. Now we apply the sec squared theta, which is equal to tan squared theta plus 1, and so apply that trig identity in, which will give us 491 out of the brackets tan squared theta plus 1 minus 2500 tan theta plus 1800. Continue that on. You multiply the 491 in to the brackets. You combine like terms, which is the 1800 and 491. And there you're given in the blue 491 tan squared theta minus 2500 tan theta plus 2291 is equal to 0. Now notice that this is in the form of ax squared plus bx plus c if we let tan theta is equal to x. If we let tan theta equal to x, we can solve for the solutions using the quadratic equation of tan theta. Then by applying an inverse of the inverse tangent on that x value, we will gain theta. So that's exactly what we did down here. We used the quadratic equation applied to solve for possible solutions for tan theta. Notice just above that, all we did was convert all the tan thetas into x's so that we could put it in our quadratic equation. Now using the quadratic equation, which is minus b plus or minus the square root of b squared minus 4ac divided by 2a, we get two solutions for x noted down on that line that states that x is either 3.89 or 1.20, which makes sense because if the position is modeled by a parabola, then it makes sense that there is two possible solutions. Now we apply the inverse of the tangent to solve for theta. So we just go inverse tangent of 3.89 grants us an angle of 75.58 degrees, and the inverse tangent of 1.20 grants us an angle of 50.19 degrees, which are our two possible launch angles. Now moving on to actually finding the range. Oops, that's the wrong photo. This is the one. Now we have to derive an expression for range time. Now range time is when the y position is equal to 0, but it is also known as double the time it takes to reach the apex. As I've noted just down here, t impact is equal to 2 times t apex. T apex is when the velocity of y is equal to 0. Therefore, if we use our equation from the start of the velocity, we have now written down that the velocity of acceleration times t apex plus initial velocity is, you can turn that into 0 is equal to minus g, which is acceleration, times t apex plus vy. Vy we know as 250 sine theta, so you apply that on following the arrows, and you get 0 is equal to minus 9.81 t plus 250 sine theta. Rearrange to solve for t apex, and you're given t apex is given to 250 sine theta divided by 9.81. And now we solve for range time, which is time impact, given by twice the amount of time apex. Therefore, we just multiply it by 2, and we get t impact is equal to 2 times 250 sine theta divided by 9.81, or t impact is equal to 500 sine theta over 9.81. Now that we have time impact, which we're just going to denote as ti for the rest of the solution, since range is only concerned with the x position, our range function, as we know from the start, is x of t is given by initial velocity times time. We can sub in ti to give us another expression, which is x of ti is equal to vx times ti. Now, our range, general range for this equation is then given by 250 cos theta multiplied by ti, which is 500 sine theta divided by 9.81. Now, the last thing for us to do is to substitute our two angles to solve for the ranges. The range of 75.58 degrees, as you can see to the left, is just there. You substitute it into the equation, which gives you a total value of roughly 3,073.17 meters. Don't worry, we will address the significant figures in the end when it comes to our answers. And all you really do is sub in these two angles into the equation above, which shows below. Same done for the angle of 50.19 degrees. 250 cos 50.19 multiplied by 500 sine 50.19 degrees divided by 9.81, and it gives you two ranges, one of which is 3,073.17 meters and the other being 6,266.78. Now, notice that the distance r we're looking for is the closest range in which the boat is protected. Now, the closest range to 2000 to about 2,800, which is the total distance from the start of the. If we go look again at the very first image, which is this one, we can see that the 2,800 is the distance from the where the projectile is fired all the way through to the shore. Therefore, our closest range here is the one given by 3,000 meters, or roughly 3,000 and something meters. Now, if we go back to the other image, we can see here that to solve for distance r, we take it's the difference between the range of this angle here, taken away by 2,800, which, if you subtract from each other, gives you an approximate value of 273 meters to three significant figures. Now, this answer may vary depending on the amount of significant figures you carried throughout the whole solution, but in my solution, I've carried it out as accordingly, as you can see, and you have here a distance of approximately 273 to three significant figures. And that is our calculated distance to the right of the mountain of which a projectile cannot hit, because within that range, either our premise of meeting the 1800 meter limit is broken, or that's the range in which the projectile cannot reach from the side of the shore. Thank you.